Hello everyone. So this lesson is about R2D2, that stands for Recurrent Replay Distributed DQM. We will go over what it is, how the architecture works, and what each part's doing on the screen here. And let's begin with what this actually is. R2D2 is a reinforcement algorithm. It is designed to deal with environments where you don't always see the full state, meaning it works well when the agent has partial observations. To handle that, it uses a recurrent neural network, specifically LSTM, which helps keep a memory of past observations. That way it can make better decisions even when the current state doesn't tell the full story. And this kind of setup is not just running on one machine, it is made to scale across multiple systems. So what you see here is a combination of recurrence, distributional learning, and a distributed training setup. Let's look at this top block. This part is showing the recurrent Q network. At the core of this is the LSTM module. LSTM stands for long short-term memory, and it is a type of recurrent unit that can maintain a hidden state over time. That hidden state is updated at each time step based on the new input and the previous memory. Right below it, we see the value distribution. Instead of predicting just a single number for the value of a state, R2D2 predicts a full distribution over possible outcomes. This gives more information about uncertainty. And you will notice the histogram here. These are predicted values spread across 100. Okay, that means there are 51 points representing different possible returns. So rather than just saying this state is worth 8, it tells us the spread of possible returns. Now down here we have got the distributed system setup. On the left you have the learner. This is the central network that's getting updated based on what's sampled from the replay buffer. In the middle we see the replay buffer itself. Okay, it stores past experiences, and importantly it does this with prioritization. The label priority alpha equal 0.6 means that the sampling favors more useful transitions, typically based on their temporal difference error. Higher errors get higher priority. And on the right, you have got the actor network. You can see each of these actors is an independent agent interacting with the environment. So some are active right now. That just means they are currently collecting experience to feed back to the buffer. The total number of actors can vary, but here we have 8. And let's go step by step through the algorithm flow now. The first step is observing the state. So what is happening here is each actor looks at the current environment state and sends that into the network. This is the start of the process. We are just grabbing observations from the environment. In the next step, the LSTM network processes that observation, but it is not just an observation on its own. It also uses the hidden state from the previous time step. That gives it a way to carry information forward, which is a key in partially observable settings. Then we move on to sampling the action. The agent doesn't just pick a random move, it samples from the Q-value distribution using an epsilon greedy strategy. That means most of the time it picks the best known action, but occasionally it tries something random to keep exploring. Now, after choosing an action and executing it in the environment, we store the result. What gets saved, it is not just one step. R2D2 works with trajectories. That means a full sequence of steps, including states, actions, and rewards. Then, when it is time to learn, we sample from that replay buffer, but not randomly. Remember, it is prioritized. So transitions with larger TD errors are more likely to be sampled, and TD stands for temporal difference. Larger errors typically mean the agent was more surprised, which makes those samples more useful for learning. Once a batch is sampled, the learner updates the Q network, and it uses these stored trajectories and updates the weights of the network through backpropagation. And finally, the new parameters are synced back to all the actors so that they are using the most recent version of the model. Okay. Let's take a closer look at this burn-in thing for a second. Burn-in is used to initialize the LSTM state before training. So when we sample a trajectory, we don't start training on it right away. Instead, we pass a few time steps, say the first 3 steps, through the network without calculating loss. This helps warm up the LSTM's memory to match the actual context of the sequence. Then training kicks in for the rest of the steps. That split you see here with burn-in on the left, training on the right, just shows that division in the sequence. Okay. Let's scroll back down and revisit the value distribution part. Again, what you are seeing here is not a single Q value, but a spread of possible returns. The x-axis here represents values, and we have, what was that, 51 of them. This could correspond to different possible rewards. The height of each bar shows the predicted probability of getting that outcome. And that full distribution gives us a better picture, especially in environments with a lot of randomness. Okay, now here's how all of this is wired together in a distributed setup. At the top, we have got the central learner. It is connected to the replay buffer and also to each actor. There are two types of communication going on here. The dotted lines show parameter sync, so when the learner has updated its weights, it sends those back down to the actors. The solid lines represent trajectory flow, that's the actor sending collected sequences back to the buffer for training. So you have got this loop, actors collect data, data goes to the buffer, learner trains, updated model goes back to the actors. And finally, just to summarize what makes R2D2 useful, first, it handles memory well. The LSTM structure means it can keep track of previous observations and use them when deciding what to do next. That's important when the current input doesn't tell the useful story. Second, it doesn't just make single point predictions, it gives you a full distribution that helps with decision making in environments that are noisy or unpredictable. And it is, because it is distributed, you can run it across many machines or processes in parallel, making it faster to train.